General Relativity and the Equivalence Principle. Main article. History of General Relativity. Black circle covering the Sun, rays visible around it, in a dark sky. Eddington's photograph of a solar eclipse. General relativity (GR) is a theory of gravitation that was developed by Einstein between 1907 and 1915. According to general relativity, the observed gravitational attraction between masses results from the warping of space and time by those masses. General relativity has developed into an essential tool in modern astrophysics. It provides the foundation for the current understanding of black holes, regions of space where gravitational attraction is so strong that not even light can escape. As Einstein later said, the reason for the development of general relativity was that the preference of inertial motions within special relativity was unsatisfactory, while a theory which from the outset prefers no state of motion, even accelerated ones, should appear more satisfactory. Consequently, in 1907 he published an article on acceleration under special relativity. In that article titled, "On the Relativity Principle and the Conclusions Drawn from It," he argued that free fall is really inertial motion, and that for a free-falling observer the rules of special relativity must apply. This argument is called the equivalence principle. In the same article, Einstein also predicted the phenomena of gravitational time dilation, gravitational redshift and deflection of light. In 1911, Einstein published another article, "On the Influence of Gravitation on the Propagation of Light," expanding on the 1907 article, in which he estimated the amount of deflection of light by massive bodies. Thus, the theoretical prediction of general relativity could for the first time be tested experimentally. Gravitational waves. In 1916, Einstein predicted gravitational waves, ripples in the curvature of spacetime which propagate as waves, traveling outward from the source, transporting energy as gravitational radiation. The existence of gravitational waves is possible under general relativity due to its Lorentz invariance, which brings the concept of a finite speed of propagation of the physical interactions of gravity with it. By contrast, gravitational waves cannot exist in the Newtonian theory of gravitation, which postulates that the physical interactions of gravity propagate at infinite speed. The first, indirect, detection of gravitational waves came in the 1970s through observation of a pair of closely orbiting neutron stars, PSRB 1913+16. The explanation of the decay in their orbital period was that they were emitting gravitational waves. Einstein's prediction was confirmed on the 11th of February 2016, when researchers at LIGO published the first observation of gravitational waves, detected on Earth on the 14th of September 2015, nearly 100 years after the prediction. Hole argument and Entwerf theory. While developing general relativity, Einstein became confused about the gauge invariance in the theory. He formulated an argument that led him to conclude that a general relativistic field theory is impossible. He gave up looking for fully generally covariant tensor equations and searched for equations that would be invariant under general linear transformations only. In June 1913, the Entwerf draft theory was the result of these investigations. As its name suggests, it was a sketch of a theory, less elegant and more difficult than general relativity, with the equations of motion supplemented by additional gauge-fixing conditions. After more than 2 years of intensive work, Einstein realized that the whole argument was mistaken and abandoned the theory in November 1915. Physical cosmology. Einstein with Millikan and Georges Lemaitre at the California Institute of Technology in January 1933. In 1917, Einstein applied the general theory of relativity to the structure of the universe as a whole. He discovered that the general field equations predicted a universe that was dynamic, either contracting or expanding. As observational evidence for a dynamic universe was not known at the time, Einstein introduced a new term, the cosmological constant, to the field equations, in order to allow the theory to predict a static universe. The modified field equations predicted a static universe of closed curvature, in accordance with Einstein's understanding of Mach's principle in these years. This model became known as the Einstein world or Einstein's static universe. Following the discovery of the recession of the nebulae by Edwin Hubble in 1929, Einstein abandoned his static model of the universe, and proposed two dynamic models of the cosmos, the Friedmann-Einstein universe of 1931 and the Einstein-de Sitter universe of 1932. In each of these models, Einstein discarded the cosmological constant, claiming that it was, in any case, theoretically unsatisfactory. In many Einstein biographies, it is claimed that Einstein referred to the cosmological constant in later years as his biggest blunder. The astrophysicist Mario Livio has recently cast doubt on this claim, suggesting that it may be exaggerated. In late 2013, a team led by the Irish physicist Cormac O'Rafirte discovered evidence that, shortly after learning of Hubble's observations of the recession of the nebulae, Einstein considered a steady-state model of the universe. In a hitherto overlooked manuscript, apparently written in early 1931, Einstein explored a model of the expanding universe in which the density of matter remains constant due to a continuous creation of matter, a process he associated with the cosmological constant. As he stated in the paper, "In what follows, I would like to draw attention to a solution to equation 1 that can account for Hubble's facts, and in which the density is constant over time. If one considers a physically bounded volume, particles of matter will be continually leaving it. For the density to remain constant, new particles of matter must be continually formed in the volume from space." It thus appears that Einstein considered a steady-state model of the expanding universe many years before Hoyle, Bondi and Gould. However, Einstein's steady-state model contained a fundamental flaw and he quickly abandoned the idea. Energy-momentum pseudotensor. General relativity includes a dynamical spacetime, so it is difficult to see how to identify the conserved energy and momentum. Noether's theorem allows these quantities to be determined from a Lagrangian with translation invariance, but general covariance makes translation invariance into something of a gauge symmetry. The energy and momentum derived within general relativity by Noether's prescriptions do not make a real tensor for this reason. Einstein argued that this is true for a fundamental reason: the gravitational field could be made to vanish by a choice of coordinates. He maintained that the non-covariant energy-momentum pseudotensor was, in fact, the best description of the energy-momentum distribution in a gravitational field. This approach has been echoed by Lev Landau and Yevgeny Lifshitz, and others, and has become standard. The use of non-covariant objects like pseudotensors was heavily criticized in 1917 by Erwin Schrödinger and others. Wormholes. In 1935, Einstein collaborated with Nathan Rosen to produce a model of a wormhole, often called Einstein-Rosen bridges. His motivation was to model elementary particles with charge as a solution of gravitational field equations. In line with the program outlined in the paper, do gravitational fields play an important role in the constitution of the elementary particles? These solutions cut and pasted Schwarzschild black holes to make a bridge between two patches. If one end of a wormhole was positively charged, the other end would be negatively charged. These properties led Einstein to believe that pairs of particles and antiparticles could be described in this way. Einstein-Cartan theory. Einstein, sitting at a table, looks up from the papers he is reading and into the camera. Einstein at his office, University of Berlin, 1920. In order to incorporate spinning point particles into general relativity, the affine connection needed to be generalized to include an antisymmetric part, called the torsion. This modification was made by Einstein and Cartan in the 1920s. Equations of motion. The theory of general relativity has a fundamental law, the Einstein field equations, which describe how space curves. The geodesic equation, which describes how particles move, may be derived from the Einstein field equations. Since the equations of general relativity are nonlinear, a lump of energy made out of pure gravitational fields, like a black hole, would move on a trajectory which is determined by the Einstein field equations themselves, not by a new law. So Einstein proposed that the path of a singular solution, like a black hole, would be determined to be a geodesic from general relativity itself. This was established by Einstein, Infeld, and Hoffman for point-like objects without angular momentum, and by Roy Kerr for spinning objects.